Okay, so every time I give a theory talk, I promise I will never do it again. But since this is in honour of Fisher, I've been tempted back. So I'm going to talk about social evolution, and in particular, how we can combine models from quantitative genetics about the evolution of multiple traits under simultaneous selection, and some classic equations from social evolution theory, in particular Hamilton's rule. Okay, so there's two main frameworks for understanding social evolution. The evolutionary biologists in the room are probably most familiar with kin selection models. And these largely follow from work of Bill Hamilton in the 60s and 70s. And they were primarily developed to understand the evolution of social traits that appear bad for the individual that exhibits them. So things like soldier casts in ants, where these individuals forgo reproduction in order to protect their nestmates, or the fact that in some birds, like these pied kingfishers, individuals actually help other pairs to raise their offspring. Okay. The quantitative geneticists in the room, particularly those from applied background, are probably more used to the indirect genetic approach, or the IgE approach. And these were developed around the same time, but independently by people like Willem and Griffin. And in these models, usually the people aren't so much interested in looking at the evolution of the social trait, but some production trait that is determined by the social traits of other individuals. So a classic IgE model is this maternal effect model. So you might be interested in pig carcass weight as a function of how much maternal care the piglets have received. Or more generally, you can imagine other social interactions, so laying production in chickens, and the degree to which that is influenced by how aggressive your cage mates are. Okay? So there's these two approaches. There is a very small group of evolutionary biologists interested in IgE models, so there is some crosstalk between these two approaches. But generally, it's little more than the kin selection folk trivializing IgEs, and the IgE folks saying that the kin selection models aren't general and they won't always work. So to give a sort of quite inaccurate and broad brush caricature of the two approaches, in kin selection models, you imagine some individual exhibits a social trait. So this could be a provisioning behavior in a bird. And this trait affects this individual's fitness. And the fitness here is simply the number of zygotes you produce. So if this is a female, it's the number of fertilized eggs she lays, or if it's a male, it's the number of eggs he fertilizes. And you might imagine that the consequences of provisioning food is negative. If I'm giving food to others, this is going to reduce my survival and my fecundity. And this individual also has a social partner, which might be something like a parent or a sibling or even an unrelated individual. And this individual provisions this individual with food and therefore influences its fitness. Okay, so usually you assume this is positive. If someone's giving me food, this is good for my survival and fecundity. So that's the kin selection model. The IgE models differ in one important respect. So not only do you allow the provisioning behavior of the actor to affect the fitness of the recipient, you also allow this individual to affect the trait values of this individual. Okay, so to make things easy, let's just imagine this is a mother and this is an offspring. Here we're saying that the provisioning behavior of the mother directly affects the provisioning behavior of the offspring. This is a direct effect. It's not because the mother's transmitting genes. Somehow this mother, the amount of provisioning I received is determining how much provisioning I go on to do. Okay? And if you know anything about birds or biology generally, you would think this is quite an unusual thing to happen. It's much more likely that the social trait in the mother, so provisioning behavior, affects some second trait in the offspring. So let's say body size. This is a tape measure, by the way. Or a tapeworm, yeah. So I think in general it's much more likely that social traits don't affect the same social trait in the recipient. They usually affect some other trait like body size. Okay. So for this reason, kin selection models, they tend to only focus on this single social trait provisioning behavior, whereas the IgE models, they tend to be multi-trait, particularly in an applied context where your social trait might be how much you get pecked by another chicken, but the trait of interest is something like egg size. And because the IgE models consider multiple traits, they also have to deal with the fact that these two traits might be genetically correlated, and how does that affect the evolution of this pair of traits. So you can sort of see that in this example, the kin selection model is a sort of special case, a simpler case of the IgE model. And because it's simpler, we have this very famous rule to explain whether provisioning behavior will go up or down, and this is called Hamilton's rule. And what it says is that if the cost of provisioning for yourself is less than the benefit to the recipient times how related you are to that individual, provisioning will increase. So you get an increase in altruism. So for those that aren't familiar with Hamilton's rule, we define the cost as this blue arrow, a negative effect of provisioning on your own survival. The benefit is a positive effect of provisioning on the recipient's fitness. And then this is a relatedness between the two individuals, which might be a half if it's parent offspring. Okay. So Hamilton's rule poses two problems for the IgE model. The first problem is that some sort of very prominent theoreticians claim that Hamilton's rule is completely general, and you don't need to worry about IgEs to understand social evolution. And that's surprising, given this seems to be a special case of this model. And then the second problem is, well, if Hamilton's rule is completely general, can we formulate a Hamilton's rule in this situation that allows us to get an intuitive understanding of how these traits evolve, something as simple as this neat little rule here? Okay, so just to deal with this first question, is Hamilton's rule completely general? So it's only general if you do one thing. So they're saying it's by generality, they're saying that to understand the evolution of provisioning, we don't need to worry about body size. So I've just grayed them out. And the only way you can make Hamilton's rule general in this context is, rather than looking at the effect of provisioning on fitness, you have to look at the effects, or the effect of the breeding values for provisioning on fitness. As soon as you refocus the analysis from phenotypes to genotypes, you get rid of any idea of causality. Okay? So rather than saying that provisioning causes fitness variation, you're saying somehow the genes involved in provisioning behavior are correlated with fitness. So you're ditching causation for correlation. And you might think, well, does that really matter? But just imagine that instead of looking at provisioning, we've just done a Hamilton's rule for body size. Okay? So now we've got this cost and this benefit here. If the genes involved for provisioning were the same genes, or in linkage disequilibrium with the genes for body size, you get a positive, let's say, genetic correlation between the two traits, and then you would get something that might look like a benefit. So you would say that body size is evolving because of kin-selected benefits, which doesn't make any sense in this example, because we're saying that the body size of the mother doesn't directly influence the fitness of her offspring at all. So I'd say this genetical Hamilton's rule is the rule that the theoreticians say this is completely general. It is completely general in that it'll tell you whether body size will increase or decrease, but it doesn't really tell you why. So just to echo Okasha, like, we wanted a description of evolution to provide insight into the causal factors responsible for it, rather than just getting the answer, has it gone up or down? So I'd say that the Hamilton's rule that people say are general is this genetic one. I would argue it's quite boring because it doesn't tell us why the trait has evolved. So the question is, can we define a phenotypic Hamilton's rule that's simple for an IgE model? And if we can do that, how do we define costs and benefits in this sort of system? And how should we incorporate the genetic correlations between this pair of traits? Okay, so this is our biological scenario. And I would say it has 5 main ingredients. The first ingredient is what's often called the individual selection gradient. So this is the effect of this individual's traits on its own fitness. We've got what's sometimes called a social selection vector. So the effects of this individual's traits on the recipient's fitness. You see this is 0 because there's no effect of body size in the mother on the fitness of the offspring. Then what's called the interaction matrix. So there's 4 traits, the 2 traits in the offspring, the 2 traits in the mother, and there's just one non-zero element here because this is the 3rd trait, the provisioning behaviour in the mother, affects the 2nd trait, body size, in the offspring. Okay. We've got the genetic variances for the 2 traits along the diagonal, and then we've got the genetic covariance between body size and provisioning summarized in this matrix. And our 5th ingredient, of course, is relatedness. So there's been 4 or 5 past attempts at trying to define a cost and benefit in this IgE model to try and put it in terms of Hamilton's equation. And I would say that those 5 past attempts, one of which is mine, unfortunately, I would say they're all wrong. They don't identify the costs and benefits correctly. And then the one I'll show today, I think, or at least hope, that it is how you should define costs and benefits in an IgE system. I won't go through all the 5 past attempts and explain why they're wrong. I'll just go through one of them just to show up some of the sort of flawed logic. So one of the attempts was simply to say that this vector here is the the cost, so the direct effect of the individual's trait on its fitness, and this here is the benefit, the effect of this individual's traits on the recipient's fitness. If you equate these 2 terms with a cost and benefit, and then get the equation for how the 2 traits evolve, you get this equation. The only reason I put this equation up is because it's really very ugly. Yeah? I don't want you to sit there and try and understand what this equation means, because I don't think it's possible to look at this equation and understand what it means. Okay? The thing is, superficially, this does seem to make sense to equate the costs and benefits with these 2 vectors. So imagine the kin selection model here, where we've just got the provisioning behaviours affecting fitness, and then we look what these ingredients look like under this scenario. We end up with this. So the interaction matrix is all 0. Everything else is scalars because we've only got a single trait. And then if we plug it into this equation and simplify it, we get Hamilton's equation. So evolutionary change in provisioning behaviour is equal to the genetic variance in provisioning behaviour multiplied by this term in brackets, which is the benefit, which we assume is the cost, which is negative, plus the relatedness times the benefit. And if the benefit exceeds the cost, provisioning behaviour goes up, and it helps the recipient but harms us. Okay, so back to our original scenario. One way you can see that this doesn't make sense to define the costs and benefits like this. Imagine we got rid of this red line here. So the only effect of the mother on the offspring's fitness is by making her offspring bigger. Okay, so there's no direct effect of provisioning behaviour on fitness. So now our benefit vector is all zeros. So we're saying now there's no benefit to feeding your offspring, which doesn't make sense from a social evolution perspective. People that work on social behaviour would not want you to say that by providing food to your mothers, that is not a social benefit. So you can see that the logic falls down in special cases, because it would say, in this instance, that we don't need to understand social evolution in order to understand the evolution of provisioning. Okay, so if this isn't the right way to do it, what is the right way to do it? So this is our original scenario, and I would say the right way to do it is to define the costs and benefits like this. Now, you're probably all thinking, Jesus Christ, this is even more ugly than the last equation. Yeah? But I think the difference is that the last equation was ugly both on the outside and the inside, whereas this is just ugly on the outside. Because this equation, although it's ugly, it has a very simple interpretation. And it's just the total causal effect of a trait on fitness. Okay? So in terms of the cost, well, let's go for the benefit because it's easier. No, let's go for the cost. So this is the total effect of, say, provisioning behaviour on the actor's fitness. So in this simple example, it is actually just this vector. It's these red arrows. Okay? That's all this horrible equation is doing. The benefit is a bit more complicated because you see there's two ways in which the provisioning behaviour of the mother can affect the offspring's fitness. It can affect it directly, and it can also do it indirectly through affecting the offspring's body size. Okay? So this horrible equation here is just basically accounting for these two ways in which this individual can affect its offspring's fitness. And this is through, although Fisher probably wouldn't like it, Saul-Wright's path analysis. Okay, so in this case, for this particular scenario, we have this black arrow times the blue arrow here, and then we're going to add this red arrow. Okay? It gets a lot more complicated if you've got feedback in the system or anything like that. But I think although these equations look ugly, they are quite simple. You just got to imagine the total causal effect of a trait on fitness via any path. And if we define our costs and benefits in this way, and we can look at, well, what then does the evolution of these two traits look like? And if you remember before, you had this very ugly equation, and now we have this very simple equation. In fact, it's just Hamilton's equation written in terms of matrices and vectors rather than scalars. And my guess is at least the quantitative geneticists in the room probably see, or are probably reminded of another equation given the notation I've used. Okay, so I think this is, for me, this is how you define costs and benefits in this system. It's consistent with the concept of causality, the fact that trait variation in me causes fitness in the recipient. And I don't think it's just by chance that the equation for evolutionary change is very simple. Is this meant to be read? Brian? No? Okay. So the equation has similarities with non-social equations developed in quantitative genetics. So here we have the breeder's equation, which is slightly rewritten. So the evolution of a single trait is a genetic variance times a selection gradient. If you want to expand that to multiple traits, we have the Landy equation, where we've got the genetic variance covariance matrix times the selection gradient. And then in a social context, we just have the equivalent of the breeder's equation is Hamilton's equation. And then the equation I just showed you, I would argue, is just the sort of social equivalent of the Landy equation. And quantitative geneticists, I think, have a good idea about when and why the breeder's equation will fail and when the Landy equation won't. So we can use the intuition about these two equations to tell us when Hamilton's equation will fail. And then just for completeness, we have what I call the boring genetical equations. The genetic Hamilton's equation, which I showed you earlier. Then in a non-social context, we have the Robertson-Price identity. So these work in a univariate or multivariate scenario because they don't distinguish between genetics and selection as separate processes. They just conflate them in this sort of correlational analysis. So they basically just say, for me, evolutionary change is equal to evolutionary change, which isn't very informative. Okay, so this is our equation. I think most quantitative geneticists are probably familiar with the implications of this, but just to go through it step by step. So we're saying that the evolutionary change in provisioning behaviour is equal to this term, which is Hamilton's equation, the genetic variance in provisioning multiplied by the cost plus the relatedness weighted benefit. But the problem is then we've got other traits in the model that are also under selection. So we've also got the effect of evolution in body size. And so this is the genetic covariance between provisioning and body size. And then this is basically net selection operating in body size. And together we can call this the indirect response to individual and kin selection on size. And clearly there's going to be many traits out there that are also under selection. So we've got to add all these terms in here. So it's clear that Hamilton's rule will fail when we have multiple traits, because it's very unlikely all these terms are going to be 0. So in our case, let's imagine that the benefit to relatives exceeds the cost for provisioning behaviour. So given Hamilton's rule, we expect altruism to evolve. But what we might imagine is that there's positive selection on size, being big is good, but this genetic correlation between the two traits is negative. And if it's negative enough, this term can actually outweigh this term, and rather than getting the evolution of altruism, we get the evolution of selfishness. So I think it's fairly clear that the phenotypic Hamilton's rule will fail to predict whether a single trait will evolve to be altruistic if there's multiple traits under selection. But what we could ask is, can we define a Hamilton's rule that tell us whether the system as a whole will evolve to be altruistic? Okay. And to do this, we need to use a concept from Bill Hamilton again, which is inclusive fitness. So this is the fitness caused by your own traits plus the fitness of relatives that can be attributed to your traits. Okay, so it's both of these terms. And you can show that the change in inclusive fitness is equal to evolutionary change in the traits in black, multiplied by this vector again, because this is the causal effect of those traits on fitness. Okay, and then Hamilton also showed that this happens to be equal to evolutionary change in fitness also. I've just shown you the equation for evolutionary change in the traits, so we can substitute that in. And we end up with this quadratic form. And this tells you 3 things. The first thing, it's quadratic, so as long as G's positive, there's some genetic variance in the traits, inclusive fitness will always increase via evolution. You can also equate this quadratic with a variance. So this actually is the additive genetic variance in inclusive fitness. So it recovers Fisher's fundamental theorem that evolutionary change in fitness is equal to its additive genetic variance. And then the third thing, although it won't be clear here, is that if you measure the distance between traits in generalized genetic distances, evolution is changing inclusive fitness as fast as it possibly can, given the genetic constraints. We can split this quadratic into 2 terms. The first term here is again evolutionary change in the traits multiplied by the effect of those traits on the actor's fitness, and we get the change in direct fitness. And then here we've got the same thing for the recipient's fitness, and this is the change in indirect fitness, so the change in the fitness of the recipient. So we can define system-wide altruism as the case where the traits evolve to reduce the fitness of the bearer, but to increase the fitness of the recipients. So that would be a system-wide altruism. And then we need some measure of system-wide cost and benefit. I haven't got time to explain why this is the way you should define them, but essentially you can define a system-wide cost as the total length of this vector and the benefit as the total length in this vector. And to cut a long story short, it's not possible to develop a simple Hamilton-like rule to work out when system-wide altruism will evolve based on these costs and benefits. Although there is one special case where you can define this rule, and I'll show that in a second. Okay, so here we've got 2 social traits. So we've got, let's say, provisioning behaviour here and nest defence behaviour here. And this fitness landscape here, this is a hill and this is the peak. This represents the effects of the traits on the bearer's fitness. Okay, so this is, in terms of your own fitness, this is the trait values you would like to have. And this black dot is where the population currently resides. The cost vector is simply the vector which points most steeply uphill for this direct fitness landscape. And we can define an equivalent landscape for indirect fitness. And you can see that in terms of indirect fitness, the best traits to have, you've increased provisioning and you've increased nest defence, because this is beneficial for your offspring. And the benefit vector weighted by relatedness, again, is simply the vector that points most quickly uphill on this landscape. Net selection is just the sum of these two vectors. So selection as a whole pushing the traits this way, so it's trying to reduce nest defense, and it's slightly trying to reduce provisioning behavior. So it's pushing these traits towards selfish values. If you look, it's climbing the blue hill, but it's going down the red hill. So from Hamilton's rule, we expect selfishness to evolve because this blue vector is longer than the red vector. Now let's imagine that this is a distribution of breeding values for these two traits in the population. We can see there's more genetic variance for provisioning than there is for nest defense, and the two traits are slightly negatively genetically correlated. If there were no genetic constraints, evolution would proceed along the purple vector, but because there's more genetic variation in this direction, evolutionary change is deflected towards the long axis of this ellipse. Okay? So now, rather than selfishness evolving, what you're getting is the traits are evolving in a way which is increasing indirect fitness. It's climbing up the red hill, but decreasing direct fitness. It's going down the blue hill. And if you let this evolutionary trajectory run, eventually what you find is that the traits evolve to very close to what optimizes the fitness of the recipients. And if you'd ignored the genetics, you would have assumed that the opposite would have happened. You would have gone to selfish behaviors. If you then combine these two fitness landscapes to get the total inclusive fitness landscape, then you can sort of see what's happening. The purple vector is pointing as fast as it can uphill on the inclusive fitness landscape, and evolutionary change is always increasing inclusive fitness. It's just hill climbing to this potentially local optimum. And then at this optimum, you can't really see it here, but there is a little bit of, there is a small cost and there is a small benefit, but they're quite small because you're close to the optimum for the recipients, and for the actors, you're in this sort of plane of low fitness, so selection is very weak. I think this hides an important point. If we just take another example, so here we have the direct fitness landscape. The population resides here. That is the cost vector pointing uphill. We have the indirect fitness landscape again. And then the benefit vector is this vector pointing uphill for the indirect fitness. The total net selection is the purple vector. The same genetics, an evolutionary response. And then you can see the evolutionary change in this example. It starts to increase the recipient's fitness, so you get altruism. Then it starts to reverse and climb this blue peak, so you get selfishness. Which again, it's just climbing the inclusive fitness landscape. It's always increasing inclusive fitness. And then at equilibrium, you end up with this scenario here, where what's happening is that the cost vector and the benefit vector are pointing in exactly 180 degrees apart, and they're exactly the same length. So the system-wide costs and the system-wide benefits are identical, and therefore Hamilton's equation does work, but the only time it works is when the population's at equilibrium, when there's a tension, an exact opposite tension between benefits and costs. So just to conclude, the genetic Hamilton's rule is general, but I would argue it's boring. The phenotypic Hamilton's rule isn't general, and it breaks down when other genetically correlated traits are under selection. But you can derive an equation that's quite simple, which I would argue is a social evolution analogue of the multivariate breeder's equation. I didn't show it. You can find a Hamilton-like inequality that tells you when the system as a whole will evolve to be altruistic, but it always depends on genetics, except when the population are at equilibrium, and then the influence of genetics disappears, and you get an equality that's identical to Hamilton's. That's it.
Hi, Jarrod. You can formulate a kin selection model, as you know, either as a neighbour-modulated fitness model or an inclusive fitness model. And you can go through those two different ways to recover Hamilton's rule. I wasn't really sure from your early diagrams which version of those you're actually using and whether the sort of the arguments interpretation you're putting together matters on which version you're using.
I don't think it matters. The IgE model is naturally neighbour modulated. Yeah, you had an individual and its fitness was affected by a neighbour, which happened to be its mother. But then in terms of the final interpretation, I put it in terms of inclusive fitness, just because I think it was easier to derive the results under inclusive fitness, where you have this inclusive fitness landscape. So it shouldn't matter which way you do it. It's just for ease of interpretation. I started off neighbour modulated, and I moved to inclusive fitness at the end.
This is a minor point, but I thought your graphs there were unrealistic. They show that as the bird does less provisioning, its own fitness can go down, whereas I would assume that its own fitness always goes up with less provisioning, and the opposite with the indirect provisioning. Yeah, so I mean, I should say these are blue tits, and I've done 15 years of work on this species, so I agree that this is biologically unrealistic. I just put these in as examples. I mean, you could imagine, for example, that this is just defence behaviour, and in terms of your own fitness, it doesn't make sense to have reduced defence behaviour because other males are coming into the territory. These birds actually also feed their partner. So you could argue that if you reduce provisioning, this is bad for you because then you don't have a partner. So there are, I can wangle it so it makes sense. Yeah. Wait.
Presumably you could generalize this further. It's a really beautiful generalization of Hamilton's rule, but could you add multiple interactants with different coefficients of relatedness into the picture?
Yeah, so I didn't. So the maternal effect model is actually all the way back here, even further. Yeah, so let's say you had two social partners, with different relatedness. You have a relatedness for partner one times its benefit plus the relatedness of partner two times its benefit. And actually in maternal effect models where let's say provisioning behaviour affects provisioning behaviour, then you've got the problem that my provisioning behaviour is determined by my mother, which is determined by my grandmother, by my great-grandmother, and so on. And I actually thought this equation didn't work in that context, and what you end up with is an infinite number of social partners going back in time, each one weighted by a half, quarter, eighth, 16th, 32th. I don't think 32th is the word. No.
Yeah, so it can be done, yeah.
Yeah.
Okay, thank you. So now we move on to the last event, and I'd just like... So I want to start by saying that I'm here because I represent the